Welcome back to Containers from a Cruising Altitude. My name is Ben Rasmussen, and in this section we are going to be talking about container specifications. We're going to keep this section brief, but it's important to have a high-level understanding of container specifications so that we understand why many container runtimes and tools can all work with one another and be interoperable. The specification we're going to be talking about today is the Open Containers Initiative. It's a light, fairly small open source project primarily founded by Docker and CoreOS, which maintains the container runtime Rocket, as well as some other companies. Their stated purpose is to create an open industry standard around container formats and runtimes. So the big question here is, why does everyone want to be OCI compliant? And one of the big reasons is because a few years back when the OCI was being formed, Docker donated their image and their runtime specification, as well as some of their other underlying runtime code, to the OCI. And because Docker obviously follows their own specifications, that means that all Docker images are OCI compliant. And this is important because in the last section, we talked about how the Docker Hub has kind of become the de facto location to store images, and a lot of companies like to distribute their officially licensed images in the Docker Hub. So official Java images and official Postgres images, for instance. So if you're OCI compliant, you can pull down any application image from the Docker Hub and be able to use it in whatever manner you want to. So the OCI is primarily two pieces, the image specification and the runtime specification. And we're going to start by talking about the 5 principles of containers that the OCI lays out in their runtime specification. So you've probably heard a similar analogy to this before, but the OCI likes to talk about application containers similar to shipping containers. So with shipping containers, there's a standard set of operations you can perform with them, like stacking them, moving them, loading and unloading them. And it doesn't really matter what's inside. You can always perform these actions. And application containers are going to be very similar. So the first principle is standard operations. There should be a standard set of operations that we can perform against images and containers that will have the same effect. And these are going to generally be performed with file system tools, network tools, runtime engine tools, so on. The containers themselves should be content agnostic. So when you perform a standard operation on a container or an image, it should always have the same effect no matter what's inside that image. So if I have a Java image or a Golang image or a Postgres image, if I run a create, for instance, on that image, I should always expect it to create a container out of that. The third point is infrastructure agnostic. So I should be able to build an image on my laptop and distribute it to a friend, or run it in the cloud, or run it on a VM with a container engine, and it shouldn't matter what the underlying hardware is. Containers should be designed for automation, so because of the previous 3 principles, we should have a very consistent runtime, and automating our environment, for instance in a CI/CD process, should be very easy. And lastly, we should have industrial grade delivery. Because of all of this consistency above and the automation that it enables, it should be very easy for either a dev shop of 14 people or an enterprise of thousands of people to distribute their application to their customers. So the OCI image specification, I would say, primarily revolves around the file system serializations. And these serializations describe how you take a blank file system and you start adding layers onto it to eventually create your application image. So if you want to create a C application that uses some network tools to do something, you might have your first layer be adding in some basic network tools. Your second layer would be adding in some basic C libraries, and your third layer would be adding in your application itself on top of those tools. And then the configuration and the image manifest, which is not listed on this slide, are going to be just general metadata about the container, or sorry, about the image. For instance, the layers that help comprise the file system, how it was archived up, and so on. And a runtime will then be able to take that image specification and be able to unpackage it into a running container. And the really interesting part about the runtime specification is the runtime and lifecycle portion of it. And this section of the specification is going to talk about how you take an application image and convert it into a running container, and how that container should act while it runs, and how, for instance, to stop it. And so this part of the specification will do things like define when I run a create command, we are going to first run pre-create hooks, perform the container creation, post-create hooks, what errors should be thrown in when, and then how to do things like at the end of the container runtime, how are we going to go about stopping it, when do we report an error during stopping, and so on. The runtime configuration is going to be general metadata, again, on how to take an image and convert it into a container. And this is going to include things like sandboxing features, which is going to help contain a process to the container itself so that it can't leak out into the host operating system. And at a high level, that's all we really need to talk about with container specifications. In the next section, we're going to get onto some of the more fun material, which is container runtime software. And just a little thought experiment. We've all heard of Docker, but try to think of other container runtimes that you've heard of.